Well, we know from the brainstem lectures the importance of the cerebellum because we know anytime we have a cerebellar lesion, we have what I call incoordination. And this is always on the ipsilateral side. So let's go through some slides here and do a general review of the cerebellum. This is a good one to start because you know we've talked about the brainstem down here, the medulla and the pons and the midbrain. And you can see the cerebellum here sitting over this space right here is the fourth ventricle. And you can see the cerebellum sitting here, and here we're looking at a sagittal view of the left side. You can see a midline portion here, which we call the vermis, and then out here we can see some of the hemispheres. And as the title shows down here, the cerebellum is sometimes called the little brain. If we look at a little more of an up higher power view, here we're looking at the right side, and this is the vermis here, and out here is what I'd call the hemispheres. And down in here we can see some of the brainstem that you should be familiar with. This would be the middle cerebellar peduncle, and I've done some dissections in here, so you don't worry about this. But this would be rostral, and this would be caudal, so the spinal cord would be down here. This looks like a little piece of the inferior colliculus right here, and you see some of the trochlear nerve. So again, this is rostral, this is caudal, this is the midline. And back when I was a graduate student and we heard about the cerebellum, we had to memorize all these little lobes or lobules of the cerebellum. You can see all these little gyri and sulci here. These are called folia. And like I said, back when I was a graduate student a long time ago, we had to name all these different parts of the cerebellum. And I put down here Lucy's deft pun, which was one way that I was able to remember some of these. I think you'll find this kind of funny, so you don't have to know this, of course. But we started out here, we called this the lingual, and then U didn't mean anything, but when lingual, Coleman, I think, was next. Deft was a good one. So it was decoive, folium, tuber. And then pun was praemus uveal nodule, so praemus uveal nodule. Now nodule, here the N, like Lucy's deft pun, so it went Lucy's deft pun, and N here was nodule. You should know the flocculonodular lobe, and this would be the nodule on the midline, and it's going to extend out laterally to the flocculus. Now this is a couple different views of the cerebellum. Again, here we're looking at the cerebellum here. We're going to look down on the top. We're going to look at this flat superior surface right here. So right here would be rostral, and right here would be rostral to caudal. And this just shows you what the cerebellum would look like if we look down at it on the top. You can see a midline area here called the vermis. It's shown much better on the posterior down in here in inferior surface, but this midline part would be the vermis, and out here would be the hemispheres. You can see on this superior surface that this vermal hemisphere demarcation isn't quite as clear. I made a little note over here about this midline vermal area of the anterior lobe. So again, this is rostral. This would be the anterior lobe. Alcohol has a very deadly effect on this vermal region. And you know the vermis is the more, medial zone, so it's involved in coordination, axial musculature, and things like that. So when people drink a lot, this vermal area of the anterior lobe dies, and they have what we call an anterior lobe syndrome of the cerebellum, and that they have balance and ataxia, which would make sense with what you know about and what we're going to talk about with the organization of the different zones of the cerebellum. Now, if we kind of look at this view right here, and remember, if we had a little cross-section down here, we'd have something that looks like this. Here would be the pyramids on the bottom. Here's the olive. Okay, so if we're kind of looking this way from the caudal end, looking up from a section through the medulla about like this, looking this way, again, we can see the hemispheres here of the cerebellum. And again, but we can really see this midline vermal area really well. Now, if we were to look up this way, okay, look kind of underneath the cerebellum, again, this would be rostral, this would be caudal. Again, we can see this midline vermal regions, we can see the hemispheres, but we can also see the middle cerebellar peduncle here and the superior cerebellar peduncle really showing well. Now, here's the nodule right on the midline, and here's the flocculus. So you can actually see that they are connected, and this would be our flocculonodular lobe. This is another area that you may not have heard about, but this is called the tonsillar area of the cerebellum. This is real important because sometimes when there's a lot of pressure, say in a subarachnoid or epidural hematoma, when there's a lot of pressure, this cerebellum can be forced down through the foramen magnum, and it's the tonsillar area that herniates through the foramen magnum. This is a great slide. I wanted to show you the flocculus. So, as you know from brainstem, this would be the left flocculus. Here would be the pyramid and the olive. And this is just a great view of the flocculus. Here's the base of the pons. Here's your cerebellar hemisphere. Now remember that this flocculus is continuous. You can't see it, though. It's continuous with the nodule, which is more medially located. Now, we can also just go through here and make a section, just kind of lift this whole thing off and look down on the cerebellum. Okay, so here's your spinal cord. This would be rostral, caudal. This would be the right side, left side. You can really see the middle cerebellar peduncle right here. Here's the superior cerebellar peduncle, and the inferior is coming up like this. So here are your peduncles. All we've done is taken off the overlying cerebellum. Now, when we look at the cerebellum, we look at different zones, as you know from the series of lectures. And all I think about is this cerebellum here is kind of shaped like a tent. And if you were just push this down, squash the tent, this would come back, this would go forward, and you kind of have our flattened view that we use in the class. And this is a flattened view here. You can see this would be rostral, this would be caudal. So here's your hemispheres out here, so this would be your lateral zone of the cerebellum. This should be your intermediate zone of the cerebellum, and here's your medial zone. We're not showing the flocculonodular though. And this is the one we've seen a lot in lecture. Lateral zone, intermediate zone, medial zone, and here schematically shown is the flocculonodular. So let's turn first, like we did in lecture, to the lateral zone, which is involved in planning. And the lateral zone is involved in planning, and we call this the cerebral. You see I made this bigger than the cerebellum, cerebrocerebellum, because it's got a lot of input that's coming to it from the cerebral cortex. Now, this input does not come to it directly, okay? This sensory information and this premotor information has to go to the pontine gray. Now, you remember the basilar pontine gray in the pons, okay? So we're going to have a corticopontine from the premotor. In premotor, we're talking about SMA, PML, probably posterior parietal, which I didn't put on here. And then from the sensory cortex, too. And sensory cortex, especially the areas 3, 1, and 2, which are getting lots of somatosensory information. Visual cortex, auditory cortex, any sensory cortex is going to come down here via corticopontine projection. So as we get ready to make a movement, we have to take into consideration all the sensory information that's being fed into cortex, and we can send it down to the pons. And we also need to take into consideration the plan that we want to make coming out of SMA or PML. So this corticopontine information comes down to this basilar pontine gray right here, synapse. So this is the first synapse, okay? This does not go directly to the cerebellum. Keep that in mind. It goes to the basilar pons. Now, you know from the brainstem series that the pons projects, okay, pontocerebellar fibers, all right, and they're going to go through the middle cerebellar peduncle. So we know that all this cortical information comes down to the pons. The pons then, via pontocerebellars, projects up here into the, in this particular case, when we're talking about planning, to the lateral zone. Now, let's look a little more closely at these cortical inputs that are starting up here. This is a good diagram because it shows, well, here's some input from the visual cortex coming down here, posterior parietal, sensory cortex, and here are those premotor areas. And they're all sending this information down into this pontine gray. Remember I said there's millions and millions of basilar pontine cells in here that have axons which then cross the midline and go through this big middle cerebellar peduncle and go out here, and when we're talking about planning, they go into the lateral zone and they end as mossy fibers. Now, since you know that the sole source of climbing fibers comes from the inferior olive, everything else that we're talking about is going to be coming in here as a mossy fiber. Now, once it comes in here, it goes through some circuitry that we have not emphasized very much, but I'll just go through it once with you slowly. Here's a pontocerebellar fiber that we just talked about. So it can come in here. First thing it can do is it can kind of turn on a deep cerebellar nucleus. Now, in the case of the lateral zone, we're talking about a deep cerebellar nucleus here called the dentate. But you can see this mossy fiber, this pontocerebellar, comes in here, sends a little twig in here, and excites this deep cerebellar nucleus. It also can go up here to a granule cell. And then a granule cell can go up and bifurcate, turn on a Purkinje cell. We'll keep it simple. And that Purkinje cell then, all Purkinje cells are inhibitory, goes down to this deep nucleus. So in the case of the planning, we're talking about dentate, you can see that it's getting excitation from the mossies, and it's getting kind of inhibited here from the Purkinje. So the final signal coming out this deep nucleus is excitatory. So here's the excitation, and here's the inhibition. So some people have said, well, if the Purkinje cell is inhibiting the deep nucleus, well, how can it send anything out? Well, it's getting some excitation here from the mossy. So I always talk about this Purkinje cell kind of sculpturing, or kind of, it's like if you started out with a big piece of clay and kind of whittled it down to what you wanted. That's what this inhibitory information is doing. Here comes the excitation. It can go up this way too. But remember, this inhibition is kind of modulating this, this excitation coming in here directly. And remember, this deep cerebellar nucleus, in this case we're talking about dentate, is going to excite its targets. Here's the inferior olive coming in here. Okay, you know that this is also excitatory. Climbs right up to the Purkinje cell. Okay, so we've got the lateral zone involved in planning, and we've got it into the dentate, okay? And then how are we going to get out of the cerebellum? Well, you know that the dentate's going to project via that famous superior cerebellar peduncle. So it's going to go forward and cross, and then you know it kind of surrounds the ruber-duber, and then it goes up to VAVL. Now, for planning, we're going to kind of just go right by the ruber-duber and go up to the VAVL. And then we're going to go back up right here, VAVL, go back up into cortex. And then once we're up into cortex, we're going to go to premotor cortex. But you know premotor cortex can jump right into motor cortex. I thought this was a good slide just to show you the dentate. You can also see the superior cerebellar peduncle here. So in the case of the dentate, when we're talking about planning, these cells have axons which are going to go forward, and then they're going to cross. And here you can see some of the midbrain, cerebral aqueduct, little of the nigra right here, a little bit of the cerebral peduncle. I thought this was an interesting view. So we talked about planning, but let's go over it again. Planning is getting information from the opposite pons, and that pontine gray, and that opposite pons is getting lots of input from planning areas of cortex and sensory areas of cortex. Once it goes through the circuitry out here, it's going to jump into the dentate. The dentate's going to project in the superior cerebellar peduncle, cross in the decussation of superior cerebellar peduncle, go up to VAVL, up onto premotor cortex, and then into motor cortex, and then we're going to start executing. Now, when we talk about the intermediate and medial zones of the cerebellum, we're going to be talking about execution. All right? So let's talk about that signal coming out of the motor cortex here, out of M1. Well, you know it's going to go down, and it's going to go via the corticospinal tract and start moving these muscles. When the muscles start moving, then we're going to have this unconscious proprioception coming up into the cerebellum over the dorsal spinal cerebellar tract and cuneo-cerebellar tract, and it's going to come into the cerebellum over the inferior cerebellar peduncle. So this same signal, as you know, that goes down to start muscles moving is going through the pons. This would be corticopontine. And then you're going to have pontocerebellars going through the middle cerebellar peduncle into these medial and intermediate zones of the cerebellum. Then we can make a correction. We're going to go out of the cerebellum. We're going to go through the superior cerebellar peduncle. Some of that correction is going to go on up to premotor and motor cortex, all right? And some of it's going to go into the ruber-duber and into the brainstem. Now, we have two zones, the intermediate and the medial zones of the cerebellum, that are receiving information from the pons about the intended movement and information coming up from the DSCT and CCT about what is really happening. Now, when we talk about the intermediate, we're going to be talking about the control of distal musculature, And when we're talking about the medial, we're going to be talking about the control of the axial and proximal musculature. So as we go through these intermediate and medial zones, we're going to talk about distal musculature, and it's going to have its own deep cerebellar nucleus, the interpositus. We're going to talk about the control of the axial musculature, and it's going to have its own deep cerebellar nucleus, the fastigial. So let's look a little bit at this cortical pontine input here. In the case, here it comes. It's coming down. Execution is coming out of area 4, primary motor cortex, or M1. Now, remember now, you have a homunculus here. You have the whole body represented on area 4. So we're going to show one cortical pontine fiber coming down in here. But remember, once it gets into the basilar pontine gray, depending upon where it's coming from, if it's coming from distal neurons controlling distal muscles, it's going to go into certain cells here that are going to go to the intermediate zone. If it's coming from certain cells here involved in controlling axial or proximal muscles, it's going to come into a pontine gray cell, a different pontine gray cell, and then cross, go up through the middle cerebellar peduncle, and this is going to go into the medial zone. So keep in mind that you have both distal and proximal axial information coming out in here, going to different cells, and then once it crosses here, it's going to go to either the medial or the intermediate zone, and they're going to go. They're going to terminate as mossy fibers. Now, also going into here, you're going to have cuneo-cerebellar and dorsal spinal cerebellar fibers too, which you should remember from the brainstem, and they're also going to terminate as mossy fibers. But remember that if these pathways, these cuneo-cerebellar and dorsal spinal cerebellars, are carrying information from distal muscles, they're going to go to the intermediate zone. If they're carrying information from more proximal axial muscles, they're going to terminate in the medial zone. So this would be distal, this would be proximal. Again, these are going to come in here and go through the circuitry, all right? So here again, this could be a dorsal spinal cerebellar fiber or a cuneo-cerebellar fiber. They're going to send a little twig to the deep nucleus. It's going to go up and go through the circuitry, come out the Purkinje cell. So let's take a look at the deep nucleus of the intermediate zone, which is the interpositus. Again, here's that darn climbing fiber coming up. Now, in the case of the intermediate zone, the deep nucleus is interpositus. Okay? So interpositus is a deep nucleus of the intermediate zone. It's concerned with sending information out of the cerebellum about distal musculature and helping make a correction. So here would be the interpositus. They go forward in the superior cerebellar peduncle cross. Now some of this is going to go back up via VA-VL to premotor and motor cortex. And some, as you can see, is just going to jump right into rubber-duber and go down to the spinal cord to start to make a quick correction. Okay? Now keep in mind, again, that all deep cerebellar nuclei are excitatory. So even though a Purkinje cell is inhibiting the interpositus, it's also getting some direct excitation from the mosses. So this is an excitatory signal that goes out the superior cerebellar peduncle, crosses, and go to the rubra if it wants to, can go back up to VA-VL, up into premotor and motor cortex. Now let's take a look at the deep nucleus of the medial zone, which would be the fastigial. Okay, so now we're talking about the medial zone. We're talking about inputs there that are concerned with proximal musculature, axial musculature. It could be coming from the contralateral pontine gray, or it could be coming from cuneo-cerebellar or dorsal spinal cerebellar tracts. But once it goes through the circuitry, it's going to go into the fastigial, and the fastigial is a little different. It doesn't send fibers ascending. It's kind of going to go via the inferior cerebellar peduncle. It's going to go to the vestibular nuclei into the reticular formation, and then they're going to go down and make a quick correction of the muscles that are controlling proximal and axial musculature. So we've talked about planning. We've talked about the information coming from the contralateral pons, and that contralateral pons is receiving information from premotor areas and sensory areas. That pontine gray information comes in here, goes through the circuitry, jumps into the dentate, and goes up the superior cerebellar peduncle back to VA-VL, up into premotor, premotor to motor. Then things start to happen. And we talked about the execution. These zones in here are getting pontocerebellar information, and those areas of the pons are receiving information from M1. Intermediate zone is going to be more involved with distal musculature. The medial zone is more involved with axial. The deep nucleus of the intermediate zone would be interpositus. The deep nucleus of the medial zone would be fastigial. Now let's look at the flocculonodular lobe. Now here, as I made a note here, you got to think vestibular. It's getting vestibular input, and it's a little bit different because of the deep cerebellar nucleus of the flocculonodular lobe are the vestibular nuclei. So this is a little bit different, okay? Keep in mind now that the inputs to the flocculonodular lobe are vestibular, and then you got a Purkinje cell sitting in here that's going to go to a deep nucleus that is the vestibular. Remember here, the Purkinje cell in this area is going to go to the dentate. Purkinje cells in this area are going to go to interpositus. Purkinje cells in this area are going to go to fastigial. Purkinje cells in this area are going to go to the vestibular nuclei. So this shows our old friends from the brainstem. So this flocculonodular lobe can receive input either directly from the vestibular nerve or indirectly from the vestibular nuclei. So this could just come on up, or it could go in here in synapse, and then it can go up. Now, you can also see that here's that Purkinje cell that's in the flocculonodular lobe. It's going to come down in here and inhibit the vestibular nuclei. So these vestibular nuclei are the deep nuclei of the flocculonodular lobe. And we know that these nuclei can send information down the spinal cord, medial vestibulospinal tract, lateral vestibulospinal tract, or you know that they can cross to the other PPRF and play a role in the vestibulo-ocular reflex. Now, let's just make sure we know that this mossy fiber coming into the flocculonodular lobe could be from the nerve or the vestibular nuclei. And again, they're going to turn on, you know that, they can turn on the deep nucleus of the flocculonodular lobe, which is the vestibular nuclei. Now, we know this right here. They can go up and go through the circuitry, and you can see a Purkinje cell right here comes down, and all Purkinje cells are inhibitory on the deep nucleus of the flocculonodular lobe, which is the vestibular nuclei. So this sets up some interesting things here that always cause problems with Med 1s. What happens if you have a lesion in the medial zone versus a lesion in the flocculonodular lobe? Well, if you're in the flocculonodular lobe, I forgot the lobe here, I got node. If you have a lesion in the flocculonodular lobe, you're just going to kill Purkinje cells. And you know all Purkinje cells are inhibitory. So if a lesion in the flocculonodular lobe, you only kill a Purkinje cell. If you kill a Purkinje cell, you're losing inhibition to the vestibular nuclei. If you lose inhibition, that side is strong. That side is dominating. Now, I know from when I taught you in brainstem, you can take it from here. Now, I got a big circle here. I got a big lesion in the medial zone, which will include the Purkinje cells and the deep nuclei, the fastigial. So a big lesion here in the medial zone and its deep nucleus, the fastigial. I don't care whether you kill this inhibitory signal here. You're killing the fastigial, which you know is excitatory because I've told you many times that all deep cerebellar nuclei are excitatory. So a lesion of the medial zone, you lose excitation. You lose excitation. And now this side is weak. This side is down. And I know you can take it from there. Well, what about the olive? Dr. Ulrich went on and on about the olive. I thought he did a really nice job talking about all the various ways that it's involved in motor learning. I think that if you are able to answer a question on the exam that the inferior olive is involved in motor learning, that's good enough for me. But don't forget that all of those cerebellar fibers are crossed, go through the inferior cerebellar peduncle, and go to all zones. Don't miss a question on the exam. where we're talking about all these inputs. We always forget these inputs. So when I list inputs in here, you know, I list dorsal spinal cerebellar tract, cuneo-cerebellar tract, pontocerebellus, and I kind of, as you'll see, I leave out the olivocerebellars. But I just always can remember that they go anywhere, they go everywhere, and, you know, I don't have to worry about it so much. Lesions, probably the most important part of the lecture. You have to know what happens as a doctor when you have lesions in the cerebellum. You might forget all these zones, you might forget granule cells, all mossy fibers, climbing fibers, but you can't forget what happens when things go wrong. And the key would be ipsilateral ataxia, incoordination. And what we've done in this course, we've lumped the kind of classic cerebellar signs. With lesions of the lateral and intermediate zones, we're not differentiating, okay? We're saying if you have a lesion of the lateral or intermediate zone, you're going to have errors in direction, force, speed, and amplitude. This is classic. You're going to have a decomposition of movement. You're going to have pass pointing or overshooting. This is incoordination. You're going to have a great classic thing here called dysdiadochokinesia. Try to supinate and pronate your hands real fast. You're not going to be able to do that. Dysarthria, well, why would you have incoordination of speech? Well, you just got a lot of incoordination, period. Intention tremor, that's going to be the one that'll probably screw you up. You'll start confusing this with Parkinson's. And intention tremor is the same thing as a movement tremor. It happens when you're moving. A Parkinson's tremor is a resting tremor, and it happens when your hand's at rest. So don't confuse those two. Hypotonia is very difficult to explain, but it probably is related to some descending control on gamma efferents for muscle spindles. So all these are lumping together under lateral and intermediate zones. A lot of these are the classic cerebellar signs. Again, they're all going to be ipsilateral to the cerebellar lesion. Now we're also lumping into medial zone and flocculonodular lobe such things as posture, balance, and nystagmus. But don't forget, with a lesion of the medial zone, you're going to have a different direction in nystagmus than with a lesion in the flocculonodular. So this kind of reviews inputs, and you can see I've left off the olivocerebellars. You just got to know those. So let's think about planning. The input is pontocerebellar, okay? The cortex goes to the pons before the pons go to the cerebellum. And those cortical fibers are sending information from visual cortex, somatosensory cortex, planning cortex, all those things go into the lateral zone. But the cortex has to go to the pons first. Then if we do the intermediate zone next, we're thinking execution, what kind of information? Again, olive's going all over. Don't forget the olive. I haven't listed it because I think you should know it. Input to the intermediate zone, again, a lot of the cortex has to go through the pons. So we're talking M1, information coming down, cortical pontine from M1 about distal muscles and, oops, I forgot, also proximal muscles. And don't forget the cuneo-cerebellar tract, dorsal spinal cerebellar tract, coming up into here via the inferior cerebellar peduncle. Now when we talk about the medial zone, again, we're talking about execution, we're talking about pontocerebellars, but the pontine gray projecting here are conveying information from M1 about proximal, okay? And then the dorsal spinal cerebellar and cuneo-cerebellar information coming up into here via the inferior cerebellar peduncle is conveying information about proximal musculature. When we talk about the flocculonodular lobe, the input, the vestibular nerve, vestibular nuclei. Now the olivocerebellar input goes all over and it's climbing fibers. All this other input coming in here, all this other stuff coming in here is mossy fiber. Now if we talk about the outputs, here the deep nucleus is dentate, VAVL, premotor cortex. Here the deep nucleus is interpositus, going to go to ruber and VAVL. Here the deep nucleus is fastigial. It's going to go mainly to the vestibular nuclei and the reticular formation. And when we talk output here, flocculonodular, remember this is a Purkinje cell. This is a Purkinje cell going to the vestibular nuclei. I wanted to show this to you because years ago we used to teach the histology of the cerebellum. I don't know, maybe Gary Lyons showed you this slide. I think it's gorgeous. But you've got these layers that are beautiful. Here's a granule cell layer. These beautiful, beautiful Purkinje cells. And this we call the molecular layer. You don't have to know this, but I thought I'd show it to you. It's a great slide. You know, I used to love talking about all this, but you know, with less and less emphasis on lecture and more and more emphasis on outside class activities, you know, we just can't teach this kind of stuff. But I know that you'll appreciate this. Thank you.